Okay, so practice problems. So which one was it?
The kinematic part B.
Okay.
Because in your answer, you use that equation for the E tangent and E phase.
Yeah.
For the the
Right.
with respect to time and velocity.
Yeah.
Plus squared over rho. But then for calculating 1 over rho, you use the formula, the y double prime over,
Mm-hmm.
etc. And then you took it at y equals 0. And then you said at y equals 0, 1 over rho equals 1. So therefore, we can just drop out this equation.
Okay.
But the radius of curvature for an ellipse isn't constant,
Right,
right?
but that's right. It's not constant. But when y, okay, so let's see. When y is equal to 1, we're talking about, yeah, I mean, I think I must have done that. I don't remember this problem exactly, but I must have done that because y equals 1 was the point that we were trying to look at in that problem. Or at least that was my, or at least that's what I thought we were trying to do when I did my solution.
Yeah, because, well, then in the second half of the solution, you switch to using.
To a different point?
I mean, maybe I misunderstood the solution,
Mm-hmm.
but then that's my question.
Okay. Well, let's look at that after. I don't remember that well enough. I'd have to sit here and.
And you don't have a solution that you.
Yeah.
So it's that standard equation for A.
Mm-hmm.
That makes sense. And then that standard equation for 1 over rho.
Yep.
And then, so you take that, but then you say F, you take F prime of 0 and F double prime of 0.
Right.
And so then you say, well, then so then 1 over rho is going to equal 1, the absolute value of -1.
Right.
Because when we use those values for 0.
Mm-hmm.
But why 0? Why can you just take
Right.
the point at 0? Because then you do t equals 3 further down.
Mm-hmm. Oh, y equals 0. Yeah, t equals 3 is that top point, right?
Yeah.
Oh, and that top point occurs when, so it's not y equals 0, it's x equals 0. So that top point is when x is equal to 0.
Oh, okay.
So I guess that's why. I mean, that was the point that we're looking at. So once you take those derivatives and find the formula for the radius of curvature, then plug in your the point that you're looking at specifically. Yep.
You don't want us to have that formula memorized as well?
No, that'll be on the test.
So what will we memorize? Just the acceleration and velocity?
There's nothing you have to memorize. I'll put any equations on the test.
All right.
Yep. Just know how to use them.
Yeah.
Okay. Any other questions about the practice problems?
I want to study on the lecture quizzes that we did from the beginning of the class.
Yep.
Where should I get those quizzes?
The quizzes?
Yeah, it should be on the test, right? Somebody.
Yeah, that's right. So if you just go back to open any of those quizzes, you can still look at all the questions and all the answers. Yeah, you can. Okay, so let's go on with where we were last time. So last time we talked about these two equations. So if you have a certain, so remember, given an angular acceleration vector and an angular velocity vector, the linear velocity and linear acceleration are given by this formula and this formula. I'm having video, okay, flap sweat from being videotaped. I have to find my happy place. Okay, all right, now we're back on. We can cut that out, right? Edit that out, okay. So these two equations are just the vectorized circular motion equations. So like, for example, these are the equations that you would use if you had some particle that was traveling around a circular path. You knew that, you knew the function that defined the change in the angular position of this particle over this circle. You could use these equations. They give you the velocity, they give you the tangential acceleration and the centripetal acceleration. So the question is, what's the relationship? Why is there this, why do we use the same formulas between circular motion of a particle and motion of a particle that's part of a rotating rigid body? And this is an important thing to recognize. If you have a rigid body, and it's rotating about this fixed point A, and you're interested in the motion of this point, the path that this point takes about that fixed axis is a circle, okay? So there's a really, these circular motion equations are really relevant in rigid body motion, okay? Every point, and if you're looking at this point, it's on a different circle, but it's still following this circular path, okay? So that's why these equations that are going to come up for rigid body motion are the same equations that you could use if you're calculating just the circular motion of a particle unrelated to rigid bodies. Okay. Okay, so now let's go into the next quantity we have to define. That's moment. And you hear it described, like when people talk about it, they talk about just a moment or a torque. But it's worth reminding yourself that this is always the moment of a force acting about a point, okay? So, I don't know, maybe you remember like when you took geometry in high school, geometry teachers get really upset if you write cosine and sine and don't put the angle down that that it corresponds to. Like the cosine and sine don't mean anything without the angle. The moment doesn't mean anything without these things. Okay? You have to know what force you're talking about, and you have to know what your about point is. Okay, so say that you have an object like this, and you define your about point. It doesn't have to be a fixed point or anything, but you just have to define what that point is. So say that you're interested in calculating the moment about this point A, and you want to calculate the moment produced by this force. We'll call this F. Okay? Then the definition of the moment has to do with a relationship between the vector going from A to F. We'll call that the rho vector, and that force vector F. Okay? So notice this rho vector changes if you change the about point, and it also changes if you change where that force is acting, right? And then the moment about A produced by that force is defined as rho cross F. Everyone who took statics with me, I defined this in statics. I think it doesn't hurt to, like anything you can do to be more systematic about writing down what your values are, I think will help you. And so a lot of times I would write these things down in a table form where, so I'd set up this table that was like P, A, rho, F, and then the moment about A. And you just go through all the forces acting on the object that you're isolating. P is the point where the force is applied. A is your chosen about point. Rho, then, you just calculate as P minus A. So you have a vector here, you have a vector here. Just take this column minus this column. F is your force vector. And then finally calculate the moment produced by that force about A as rho from this column crossed with F. I think that's a nice way to do it, and I can give you a lot of nice, useful mnemonic devices to remember this. I spend, like every semester, I probably spend 6 hours coming up with mnemonic devices for this. So I've come up with like 40 more since you guys took statics with me. Here's a good one. Professional aquanauts row for money. Okay, so that's just to remember the order of these things. So this is the Greek letter rho, you know. So all these mnemonic devices have rho in them. Here's another one. Princeton athletes, rho for mommy. Okay, so anyways, if you get in the habit of setting this table up, I think it seems sort of like a waste of time, but you're never going to be really under a time crunch in this class. And for the most part, whenever you're doing this, you're a lot better off slowing down and not making mistakes than speeding up and making mistakes every fifth calculation you do, you know. So, Any questions about calculating the moments? So, and the nice thing about this table is, another nice thing about this table is, so you go down, you write down all your forces, right? You have a force here, a force here, a force here, right? Say you have 3 forces acting on the body. When you're done filling out this table, you have all your forces right here, and these go right into Newton's second law. And then you have all your moments here, and these go into rotational Newton's second law. So it's just a nice systematic way to get things written down. I'm not going to, I don't require that you do that, but I would recommend trying it, see if you like it. It also is a nice way to remember what the meaning of this row vector is. I mean, I know it's easy. Like, for example, you don't calculate these moments for a few months or, 1 semester. Maybe you take some other kind of class. And then the next time you come back to it, you don't remember if that row vector is supposed to go from the force to the about point or vice versa. Okay, this is a way to remember that kind of stuff and make sure you do it right. Okay, the last thing we have to calculate before we go into rotational Newton's second law is the mass moment of inertia. You hear this described as just the moment of inertia. The same way people talk about a torque or a moment. People say moment of inertia. This is the mass moment of inertia about a point. So about a point, you need to know this or you can't calculate it. The mass moment of inertia, so what's the meaning of this mass thing? The people who are taking deform right now, we haven't gotten to it yet, but in deform, we'll use a calculation called the areal moment of inertia. It looks similar in a lot of ways, but it calculates a totally different thing. And to make it even more confusing, we call this IA. Okay, so this quantity that we're going to use in dynamics, the mass moment of inertia, is going to be called capital IA. And this different areal moment of inertia is also called IA. And they mean totally different things. One's a resistance to deformation. One's a resistance to rotation. Okay. So that's why figuring out whether you're talking about mass moment of inertia or areal moment of inertia is important. We've been defining all of these angular quantities in terms of analogs with the translational quantities, right? The moment of a force about a point is like the rotational analog of force, right? The angular acceleration is obviously a rotational analog of acceleration. Mass moment of inertia is a rotational analog of mass, okay? So in rotational Newton's second law, it's in the same spot in the equation that mass is in the translational one. And you can think of this as an object's resistance to rotational acceleration. So that's why you get more points for doing flips like this in gymnastics. Than for doing flips like this. Ooh, look how skinny his legs are. This is a very high moment of inertia about the person's center of mass. And this is a low moment of inertia. It's easy to get this shape rotating. It's hard to get this shape rotating. Okay. So what do you think is what's the important, what makes this harder to get rotating? Do you have a feel for that? I know you've talked about moments of inertia in physics before. Yeah, it's how far the mass is distributed from the center of mass. Like how much of the mass is far away from the center and how much is close to the center. Here, all of the body's mass is close to the center of mass, so it's easy to accelerate angularly. Here, the head and the feet are far away. So the mass moment of inertia depends on how far, oh yeah. Oh, geez. How far mass is distributed from the about point. The definition is an integral definition. The moment of inertia about A is equal to the integral of r squared times an increment in mass, where r is the distance of that increment in mass from the axis of rotation. So if you think about what this integral would give you in terms of units, the SI units for a moment of inertia are going to be kilogram meters squared. And this is an important fact about it that comes from this integral definition. You can add and subtract moments of inertia as long as they're calculated about the same point. Okay. You can't add or subtract them if one's calculated about something over here and one's calculated about something over here. So mathematically, that says the moment of inertia about A total is equal to the moment of inertia about A of one piece plus the moment of inertia about A of the second piece, and so on, where you can think of like Um, so if you're trying to calculate the moment of inertia of this thing about this point A, okay, you can break it up into a piece there, a piece there, a piece there, and a piece there. Okay, which is nice because they're, you know, like in this case, this is, you can break this up into 4 rectangles, and rectangles, it's really easy to calculate the moment of inertia. You know, we don't have a formula, like you can't look online and describe a crazy shape like this and figure out what the moment of inertia is, but it's easy to calculate for rectangles. So if you can break up any shape into a bunch of simple shapes, it's easy to calculate the total moment of inertia. Okay. Any questions about that? So let's do an example using the integral formula, and then I'll give you the simple shapes that pretty much, if you have to use the integral formula at all in this class, it'll just be for one of the problem sets, like a more complicated problem, but you won't ever have to do it on a test or practice problems or anything. So what's the moment of inertia about the center of a disk with radius capital R and a mass M? This is one of the formulas that we're going to use, but let's just do one integral calculation, figure out what this is. Okay, so there's the disk. Here's the center. The definition says we need to come up with some expression for an incremental, you know, like an infinitesimal mass. So let's think of, like, at some arbitrary distance, lowercase r from the center, let's think about the mass of this little, you know, thin ring. Okay, so we'll call this distance lowercase r. This disk has some thickness, right? And there's a relationship between the area of any part of this disk and the mass of that part of the disk, right? Multiply the area times the thickness times the density of the ring, and that gives you the mass of that piece. So this increment of area is equal to, you can think of stretching this ring out into a thin strip, and then it's going to be the circumference, so 2 pi r times dr. That makes sense, right? And so the corresponding increment of mass is equal to the density times the thickness times this area. So 2 pi rho t r dr. And none of these things vary with r. Right? The only things that vary with R is R itself. Yeah, that's right. Right. That's worth saying, I suppose. So yeah, that uniform density is the same thing as saying this is a homogeneous body. Okay, so then the moment of inertia about the center is equal to the integral of r squared, this is just straight from the definition I gave you, times this increment in mass, 2 pi rho t r dr. And what's the range of r? Yeah, exactly. So you can pull most of this stuff out, 2 pi rho t, and you have the integral 0 to big R of r to the third dr. So you get 2 pi rho t times r to the fourth over 4, evaluated from 0 to big R. And you get pi rho t big R to the fourth over 2. We don't know what, like, when I gave you the values that we have, I gave you that radius r, that's in there, that's good, but I also gave you this mass. So we need to express all this other stuff in terms of the mass m instead of the density and stuff. But the mass of the whole thing is equal to pi r squared times the thickness times the density. So the moment of inertia about the center is equal to mass r squared over 2. Any questions about that? So that's just one of the handful of simple shapes that you're going to use to build up more complicated shapes. I actually, the first time I did this calculation, I did it like I broke the disk up into 4 pieces, and my increment in mass was like this. So this boundary is like, and I had to use like integral tables and all this stuff. I had like 2 pages of notes. So don't do it like that. But you get the same answer, so that's good news. Okay, so usually you won't have to use integrals. So I have 4 simple shapes here. And because of the way these are drawn, I need to point something out first that I think you probably are sort of aware of already. So what's the moment of inertia of this? Like, are things distributed, is mass distributed far from the axis, or are things close to the axis? Well, it depends what axis you're talking about, right? This is going to have a relatively big moment of inertia about this axis and a relatively small moment of inertia about this axis. Okay. when you're doing full three-dimensional problems, actually the moment of inertia is a matrix. It's not just a value, because it has to take into account all these possible, axes of rotation. In 2 dimensions, you can treat it like it's just a number. But so when I give you these 4 simple shapes, I'm going to have multiple axes drawn, and that shows you, to correspond to multiple values of the moment of inertia. Okay, so the first one is a slender rod. So let's say there's an axis here, an axis here, the moments of inertia about y and z are the same. And it's 1/12 times the mass times the length squared. What if you wanted to calculate the moment of inertia about x? Well, actually, it isn't like, that doesn't really seem like a disk, but it's just a really thick disk, right? So that formula that we just calculated, you would use that value if you want to calculate the moment of inertia about the x-axis here. A thin rectangular plate. So let's call this the x-axis, this the y-axis, and this the z-axis. And call this length C. And this length B. Then the moment of inertia about x is equal to 1/12 mass times b squared plus c squared. The moment of inertia about y is 1/12 mass times c squared. Because if you're rotating about the y-axis here, it's really the same thing as rotating a slender rod with more mass, with mass proportional to how far down it drops. And then moment of inertia about z, 1/12 mass b squared. I think maybe you sort of notice as you go through these that this is the start. This is kind of the first thing in this class where you're going to have to do some just kind of three-dimensional thinking. Like what's the shape of this thing relative to this axis? Okay, thin disk. Does it have to be thin? It has to be. I don't have that formula here. I better get that for you. So the one that we just calculated is a disk rotated about this axis. Okay, so we know what the value is for the moment of inertia about the z-axis. That's the one we just calculated. That's mr squared over 2. But I don't seem to have the other two written down. I'll have to get those. Yeah, that's right. And so this says a thin disk. The thin is required for these two. It doesn't have to be thin for the rotation about the center. Okay, so using the sum formula, you can build up complicated shapes from these simple shapes. And actually, even in like biomechanics, you'll see people build up, you know, if you're trying to do some calculation of what's happening with the arm, you know, you break it up into a cylinder here, these things that you can calculate the moments of inertia for, and treat the body as a, you know, whatever level of detail you need, you break it up into that many pieces, you know. So you can get really complicated shapes.
Moment of inertia of that is 1/4 mr squared.
Oh, for this? Thank you. Great. So the question is, you know, the formulas that I gave you, they're only for, like if you look back at where I put all these axes, they're only for rotations about each object's center of mass. So, I mean, you'd have to think there are a lot of cases where you want rotations about something else. Does that make these formulas useless? Because that would be a big problem, you know. Yeah, exactly. I mean, so right. In order to use the sum formula, you have to have your individual moments of inertia about the axis that your total thing needs to be about. So how do you use these to calculate moments of inertia about other points? And it turns out there's a really easy correction, and that's lucky because otherwise, you'd have to, I suppose otherwise you'd have to use that integral formula most of the time. Formulas just wouldn't be very useful. Anyone remember what this correction is? Remember what it's called? Let me jog your memories. It's related to parallel axes. Yes. Okay, so the correction for translating axes of rotation What? Oh, yeah, I got distracted by not knowing that. Here, just do this with your... Okay, yeah, the last one is a sphere. And all axes, you can imagine, are the same to a sphere. X, Y, and Z. And they're all equal to 2/5 m r squared. Okay, so I have a question. Why? So think of this rotation about the z-axis. Why is that different? You can see it's pretty close to the same thing, but why is that different than a rotation of a disk about the z-axis? Does that make sense to you that those would be different? Okay, so yeah, when the fact that this is a three-dimensional shape, the mass bulges out close to that axis of rotation, means you would expect that mass is distributed in a way that more of it is close to the center than the disk, right? So you'd expect it to be a little easier to rotate a sphere about that axis than it is to rotate a disk circular, about that circle. And that's what you get. It's a little bit easier to rotate the sphere than it is to rotate the disk. Once I make this change, there'll be no record that I ever made this mistake. Oh! Okay, so the correction factor for translating the axis of rotation is called the parallel axis theorem. And for the people in D form, I'm just setting you up for, like, this can get really confusing. And I know, like, I've talked to a lot of people who've, I remember talking to someone, a really smart engineer, like, with a master's degree in something, and, you know, it had never been stressed and never come up, and, you know, she didn't do a lot of work with this stuff, so it never really mattered to her. But like years after finishing engineering school, she was like surprised to, like, oh yeah, those two things are different. Like, it had never occurred to her, like, the two moments of inertia are different. And I think that's pretty common, you know? So the people in D form, I'm just trying to be, I want to be clear about this. So parallel axis theorem, there's also a parallel axis theorem that looks identical to this parallel axis theorem for the other moment of inertia, just to make it harder. Well, really not to make it harder, really just because it's mathematically true, but it does make it harder. Okay, so say that you have this shape, and say this is the center of mass. And you know the moment of inertia about this point. Okay, so let's call this axis C, because it goes through the center. And say that what we want to know is the moment of inertia about this point, about an axis going through this point that's parallel to this one. We'll call that axis A. And say these axes A and C are parallel. Okay, so let the axis C be parallel to A, and C passes through the center of mass. Then the moment of inertia about A is equal to the moment of inertia about C plus the mass of the object times the distance squared, where this is the distance. Okay, so this is the parallel axis theorem. And notice one thing it says, so notice, the moment of inertia is, no matter what direction the axis points, okay, the moment of inertia is always smallest when it passes through the center of mass. This thing can't be negative because of the d squared. Any questions about that? Okay, so let's do an example problem. So say each of these distances is 1 meter. And then this is 2 meters. Okay, and say right in the center side to side, there's a removed circle here. And say this distance is 2 meters. And let's say the thickness is 0.2 meters. And the density of this shape is 3,000 kilograms per cubic meter. And let's call this axis A, and this axis B, coming out of the page. And the question is, first, what's the moment of inertia about A of this shape? And second, what's the moment of inertia about B of this shape? Okay, so for the first one to calculate, I mean, really the overall strategy is the same for both of these. What do you think? What's our strategy? So yeah, we're going to think of it as a big rectangle because we know the formula for that moment of inertia. We're going to remove the moment of inertia for the circle. Okay. So we're going to calculate the moment of inertia of the rectangle about its center. We're going to use parallel axis theorem to translate it down to here. We're going to calculate the moment of inertia of the circle about its center. Parallel axis theorem to change the axis to here. And then we're going to subtract those two. Okay? So it's a sort of a bunch of steps, but conceptually, it's not too hard. Okay, so for part A, first we want to calculate the moment of inertia, let's say, I'm going to call this point CR for rectangle, and I'm going to call this point CC for circle. So let's start with the rectangle. The moment of inertia about the center of the rectangle. So what's that formula going to be? Like look back at the definitions of or those four formulas. IX. This is A, so it's like, this is going to be like Y, okay, or Z. So we're going to go 1/12 times the mass. And the mass of the rectangle is the density times the thickness times the area of the rectangle. we're ignoring this circle to calculate the moment of inertia for the rectangle. So 4 times 2, so we get, what's that, 1.6 times 3,000 is 4,800 kilograms. Okay, so 1/12 times the mass times the length. Which length do we want for this one? See, this is the like three-dimensional thinking that it can be like, it can sort of catch you off guard how easy it is to mess these calculations up. But what did I ask you? Oh, what's the length we care about? It's this length. Okay, we're thinking about an axis going through like this, right? So the thing that matters is how far is the mass distributed from that line, okay? And what matters in that case is the 4 here. It's the whole length.
Because of the parallel axis.
We're not getting to the parallel axis yet.
It's the rounded A, right? With the 4.
I don't know what's the around the center, but it's not like,
We're doing it around this red line, but it's the sort of like the perpendicular length of the whole object. We're not doing the circle. I mean, it's the whole length of the side. Oh yes, I see what you mean. Yes, that's right. That's right. Yep. Okay, so 4 squared. Can someone calculate that? Or did someone already? $65. Okay. Kilogram meters squared. And parallel axis theorem then says moment of inertia about A is 64 plus 4,800. The distance is 2. Wait, is this 6,400? It seems like it would be bigger because you have 4,800 times 16 divided by 12. 6,400. Ah, I was only off by a factor of 100. Okay, and then what's this when you add the parallel axis theorem? Okay, so notice in this case, the much bigger part of that moment of inertia is coming from the parallel axis theorem. And you can have shapes, you know, you'll have problems where the moment of inertia of the shape itself has almost barely even appears in your final calculation. It's all parallel axis theorem. It's all just how far this shape is moved from the axis. Okay, so there's the moment of inertia of the rectangle about A. And now calculate the moment of inertia of the circle. Its mass is pi times, the radius is 0.5. Times the thickness times the density. And can someone calculate that? I don't have that. Is that right? That seems small. Oh, okay. 471.2 kilograms. Okay, so now we're going to calculate the moment of inertia of the circle about this line. So which formula do we need for that? Oh, good. JP, I'm glad you came up with that formula because we need it for this one. I guess I have it here. Okay, so the moment of inertia about the center of the circle is mr squared over 4. So we have 471.2 times 0.5 squared over 4. And that one I have as 29.45 kilogram meters squared. And now the parallel axis theorem says the moment of inertia about A is equal to 29.45 plus md squared. What's d for this? 3, yep. So 29.45 plus 471.2 times 3 squared, and I think you get 2974.69 kilogram meters squared. So now combine the two shapes. And you get that the total moment of inertia about A is 25,600 minus 2974.7 is 22,625.3 kilogram meters squared. And if you remember back to, last class I introduced the form of the rotational Newton's second law that we're going to see. And I said there are two cases, right? There's a case where nothing's fixed, and then you have to have all your about points be the center of mass, right? And then there's a case where you have a fixed axis, like a pin joint or a hinge or whatever. And in that case, all your about points are going to be that fixed axis, that fixed point. So when would you have to do something like this? You'd have to calculate this moment of inertia if this shape had a pin joint in line with A here, okay? you'd calculate this moment of inertia so you could use it in rotational Newton's second law for something that's going to rotate about A. Any questions about that? Who thinks this is pretty awesome? Half? Good. Okay. So we don't have time to do that second one. I guess maybe we'll start with that next time, and that'll be on next Tuesday. So, because the test is Thursday. So that'll, give you a chance to sort of, I think I'll probably have you guys do that, and it'll give you a chance to kind of remind yourself what we were working on. And then the next topic, so after we finish this example, we're going to get back to the rotational version of Newton's second law. And once we do that, we're going to be able to do all sorts of rotational kinetic problems. Okay, that's it.